Hey everybody, today we're learning about what makes something an acid or a base. So the first thing we're investigating is what acids and bases actually do. So one way of representing what they do is to put water over the arrow. Water is always necessary because to have ions exist, you need water to keep them apart. And so then you would just show that the hydrogen and the anion, which is whatever's with it, that's just generic, are separating. So the anion could be something like acetate, or a more correct way to write it would be including the water as a reactant. So then the hydrogen ion is going to go right over to the water and form hydronium. For a weak base, you've got to have the water because it can't make hydroxide on its own. So we're going to have one of the hydrogens being attracted by the anion. When the hydrogen comes off, then it forms hydroxide. So the anion could be acetate, or we could be still calling it A-, but it could be another weak base like NH3, where it can accept to H+, just like an anion can, but it's not actually charged. Next, we're going to look at the different types of acids and bases, so classifying them. So we have Arrhenius, Bronsted-Lowry, and Lewis. The Arrhenius definition is the oldest one that you're probably most familiar with. I remember it as A comes before B. So Arrhenius acids make H+, which then turns into hydronium. Bronsted-Lowry, same deal, make H+, which turns into hydronium. Lewis acids we haven't learned about yet. They're defined with electron pairs, so Lewis acids accept an electron pair. And they use that electron pair to make a covalent bond where both electrons come from the electron pair they're accepting, both electrons in the bond. Bases, Arrhenius makes hydroxide. Bronsted-Lowry accepts H+. So Bronsted-Lowry acids make H+, bases accept H+. Lewis bases donate an electron pair. Let's look at some examples. Arrhenius would be some things like HCl or NaOH. Bronsted-Lowry would be HCl for acids. NaOH could work actually as a Bronsted-Lowry base because hydroxide can accept to H+ and turn into water. And then a more typical Bronsted-Lowry base is NH3 because it can accept to H+ and turn into NH4+. Some Lewis acids that are common. Cations like Al+3, Tin2+, Lead2+, other transition metal ions. Bf3 is a classic Lewis base. That's how they started out, as saying Lewis bases Lewis acid. That's how they started out, as saying the only Lewis acids are things that are trigonal planar and have basically a space where another electron pair can go, like Bf3. And oxides of nonmetals like CO2. Some examples of Lewis bases: hydroxide, cyanide, acetate, NH3, H2O, things that have electron pairs. So these ones obviously do because they have a negative charge. NH3 has a pair of electron pairs on the N if you draw the Lewis structure. H2O has two pairs of electrons on the O if you draw the Lewis structure. So those are just the most common Lewis bases. Okay, next we're looking at whole reactions instead of just individual chemicals. Really, this is a repeat of the previous slide, so I don't know how much you want to write down, but you just look at each thing in the reaction and decide what kind it is, and then classify the whole reaction based on its parts. So we're going to compare each reactant to the product it becomes. So if it's losing H+, that's an Arrhenius acid or Bromsey-Lowry acid. If it's losing hydroxide, that's an Arrhenius base. If it's gaining H+, that's a Bromsey-Lowry base. Okay, these are worth writing down for sure. If you're combining a Lewis acid and a Lewis base, it's a Lewis acid-base reaction. And if you're forming a complex ion, it's a Lewis acid-base reaction. So the way you solve Lewis acid-base reactions is you just combine them into one chemical. They always form a covalent bond and go together. Or a complex ion, if you see a complex ion forming, it's the same thing. Two things are combining, but it's usually less obvious by looking at the reactants what they are. So an example is aluminum and water combining to make a complex ion. See how it has the Lewis acid, Al+3, it has Lewis base, water, and the whole thing still has a charge. That's called a complex ion. When you have metal ion, common attachment called a ligand, it's a Lewis base, and then the whole thing has a charge. Okay, this is probably a most important slide. We're looking at knowing if something is acidic, basic, or neutral just by looking at its formula. So, if you have a strong acid, it's very acidic, like HCl. If you have a weak acid, then it would be acidic, less acidic than a strong acid for the same concentration, like acetic acid. Strong base, very basic, like KOH. A weak base would be less basic for the same concentration, like NH3. So those are pretty obvious. And then we have the ones that are a little bit less obvious, like the anions. Anything that's an anion has a negative charge, so it can accept a H+, which makes it a Bronsted-Lowry base. So those are basic, like oxide, carbonate, bicarbonate, all those things can accept a H+, that makes them Bronsted-Lowry bases. But there's some exceptions. Some things are really bad at holding on to H+. The exceptions are chloride, bromide, iodide, nitrate, hydrogen sulfate, perchlorate, and chlorate. There's 7 of them because those are the conjugate bases of the strong acids. If something's a strong acid like HCl, that means all the H+ comes off in water. That means the Cl- is not good at holding on to a H. So that means that Cl- will not accept a H and act like a base. So the conjugate bases of the strong acids, those anions are not basic, just neutral. Okay, and then the Lewis acids that we mentioned earlier, Al, tin, lead, and transition metal ions, those ones are Lewis acids, so they're acidic. Here's an example of why it's not totally obvious. In water, Al+3 reacts to form a complex ion with 6 waters on it, but then one of those hydrogens its bond is weakened and it comes off. So you get 5 waters and OH that's left from the 6th water, and then the H+ comes off. So that's why these guys are Lewis acids, is because in water they make H+. Okay, finally for today, we'll look at some of those bond strengths. So if you have a more polar bond to hydrogen, that makes the bond stronger. So that makes the H separate less. So that makes it a weaker acid. If you have a stronger bond, that means the H separates less, so it's a weaker acid. And lastly, if you have an electronegative atom close to the bond, it weakens the bond because then the electrons that are bonding the hydrogen aren't evened out in the middle of the bond. They're not most stable. They get drawn a little bit towards the electronegative atom. So the hydrogen then separates more. That makes it a stronger acid. An example is comparing these two structures, similar structures, but the one on the left has a oxygen, a second oxygen next to the OH. This one just has a OH. So this oxygen there draws all these electrons toward it, which destabilizes the OH bond, makes it weaker, so the H comes off more, so it's more acidic. Which you can tell just by looking at the names. The one on the left is acetic acid, the one on the right is ethanol. So having the O there makes it even called an acid.